All right, so there's a little bit left. We didn't finish up in 8.2. And remember, 8.2 is law of cosines. Well, there's an application for law of cosines, and it involves finding the area of a triangle. I'm going to show you guys two formulas for finding the area of a triangle. One of them comes from law of cosines, so that's the connection with what we just did. The other one is different, but they're both area of a triangle, so we'll look at both. What's the formula that you learn in geometry for area of a triangle? Yep.
It's 1/2 base times height.
Yep, it's 1/2 the base times the height. And that's a great formula, as long as you know the base and you know the height. But the problem is, if you had a triangle like this, where I gave you all the sides of it, you might not know the height. If you were to draw that out, it might end up looking something like that. So just because you know all three sides doesn't mean you know the height. Or, if you had something like this. Here's a triangle where you don't know all three sides, but you know two of the sides and an angle. Well, we call 12 the base, that's fine. But 3 is definitely not the height, because it's not straight. So how do we find the area in that kind of problem? Well, that's what I'm going to show you. All right, so let's take a look at that triangle. So what I've drawn here is, I just get rid of this at first. I've drawn a triangle, and I labeled the sides A, B, and C, just like we always do. And I labeled some of the angles across from those sides. I put alpha across from A, and I put gamma across from C. That dotted line that I just drew, that's the height. And side B, that is the base. So you know the base in this formula, but you do not know the height. You might be given either the A or the C, but I'm not going to give you the H. So how are we going to find the area of the triangle? Well, let's see if we can just look at this half of it for a second. This angle right here would be 90, because the height is always drawn straight down. And I'm going to circle the three things that I have labeled in that part of the picture. Gamma, the height, and A. And what I'm going to do is I'm going to come up with a formula to solve for the height. So I'm going to do a substitution for this. I'm going to substitute in a formula that will find the height for me using these three things. So from gamma, what position is side H? Yep, that's opposite. And what position is side A? That's your hypotenuse. So what trig function could I use? Sine, cosine, or tangent? And it's going to involve opposite and hypotenuse. Yeah. Sine. So let's write that down. So sine of something is going to equal a fraction. Quinn, what's my angle that I'm using as kind of my reference point here?
Gamma.
Yeah. So it's going to be sine of gamma, which gamma will be given to you in the problem. So you're going to know that. Sine of gamma equals opposite over hypotenuse. Lucas, what's opposite, or how did we label the opposite?
Height.
Yep, height, which you are not going to know. They're not going to tell you that. And then over the hypotenuse. What's my hypotenuse? Yep. A. They are going to tell you A. So let's get H by itself. and I want to know what would go in that box. The height is equal to, yep,
Sine beta times A, or A times sine beta.
A times sine. That's it.
Gamma.
That's
Yeah,
it.
gamma.
So yeah, there we go. So let's fill that in right there. And now we have a new formula for the area of a triangle that's basically 1/2 base times height. It just uses trig to find the height when you're not given the height. So the new formula is 1/2 BA sine gamma. And usually they put the letters in alphabetical order, because remember, when you multiply two things together, it doesn't matter what order you do it in. So whether you do B times A or A times B, it's fine. But alphabetical is usually the way they write it. So 1/2 AB sine gamma. That's a new formula for finding the area of a triangle. But it's really based on the one that we already know. Now, like the law of cosines, it's more about the pattern of the letters than it is about the letters that you use. Look at the two letters that we used, and then look at the angle. In this diagram, where is this angle in relation to those two letters? Yeah, it's in between them. And that's the pattern. So what if I did something like 1/2 BC? What do you think would go in for my angle? Yeah?
No.
Alpha. Or if I did 1/2, what haven't I used? I did the A and the B and the C. I didn't do the A and the C. What do you think the formula would be there? 1/2 AC. Yeah?
Yeah.
Sine beta. So what's the pattern here in general? If you wanted to just kind of describe, don't give me any specific letters, just describe the pattern that you see in each one of those formulas. Yeah.
It has two sides and an angle.
You gotta be a little bit more specific, because you can't just pick any two random sides at any angle. You gotta follow a pattern. Yeah?
Two sides and the angle that's between them.
Okay. I see a little bit more up there than that, though. Yeah?
Wait, are we just describing the equation?
Yeah, I want you to describe exactly what these equations, I want you to describe the pattern in all three of them. So we're a little bit closer with that.
You take half of the product of two sides and then multiply it with the sine of the angle that's between them.
Exactly, that's the pattern. It's half the product of any two sides times the sine of the angle between them. It's almost exactly what I wrote. The area is half the product of the two sides times the sine of the angle between the sides. And I wrote down all three versions again, but it's not important to know the versions, because maybe I'm not going to use A, B, and C when I draw a triangle on the test. Maybe I'm going to use X, Y, Z. So whatever letters you have, take half the product of two of the sides times the sine of the angle between them. And by taking the sine of the angle between them, you're really calculating the height. So it's 1/2 base times height at kind of the foundation of this one. Yeah.
The sides, should they be in parentheses?
No. Why would you think? Well, what you're thinking? What do you?
Because I mean, like order of operations wise, would it be like 1/2 times B times C right there?
So you basically have this times this times this times that. So you're multiplying four things together. If I do 1 times 2 times 3 times 4, or 4 times 3 times 2 times 1, would I get the same thing? It doesn't matter what order you put them in. That's generally the order you write the formula in, but you can multiply in any order you want.
Okay.
But you just have to multiply all 4 together. Okay. So any question on the pattern? Yeah?
How do you know when to use which pattern? Which equation?
Well, they're all the same. In fact, I'm probably going to give you a triangle, and I'm not going to label anything in it. So you don't know what side is A, B, or C. So you don't necessarily know what version of the formula you're using. But that's not the important part. The important part is the idea of the formula, not the actual letters that are in it. So,
sure, but how do you know when to implement this then?
well, if I ask you to find the area of a triangle, right now that's the only formula that I've taught you, so you have to use that formula.
Which the A?
The 1/2 the product of the two sides times the sine of the angle between them.
Okay.
So whatever you're given.
Yeah, but how do you know what you're getting if the angles aren't labeled?
Because these labels, I mean, you could call this X, Y, and Z if you want. As long as you know two sides and the angle between them,
Okay.
you can call them whatever, call them whatever you want. Because the idea of the formula doesn't have any specific names in it. That's why, like, when I ask people what Pythagorean theorem is, they always say a squared plus b squared equals c squared. That's not really the Pythagorean theorem. That's one way of representing its specific letters. But the idea of the theorem is hypotenuse squared equals leg squared plus leg squared. Call them whatever you want. It's the idea, not the specific letters you want to remember.
Sure. So like scroll down a little bit. So that angle is theta, right? Not
Sure.
Not.
Alpha, beta, it could be anything, but it's an angle.
Okay. Never mind.
So yeah, that could be anything you want. But the question now is, do we have the information that we need to apply this idea? What do you think? Yeah?
Yes.
Yes, because according to the formula, what is it that you basically need to use this formula? Yeah?
Two sides and the angle between them.
Exactly. He didn't say anything about names. He said you need two sides and you need the angle between them. And that's exactly what they give you in this picture. Two sides and the angle between them. Okay. So how would we set up a formula for the area using that information? Next.
You would set up with 1/2 times 3 times 12 times the sine of 105 degrees.
So 1/2 the product of two sides times the sine of the angle between the sides. Here I put parentheses because you obviously don't want to just put 3 and 12 next to each other like that. So either put a dot between them or put parentheses, but yeah. All right, so let's do it up. So it's easier for me to do half of 12 first, which is 6, and then 6 times 3 gives me .
Oh, were you asking us?
Yeah, 6 times 3 gives me 18. So we get 18 sine 105. At this step, you have to type it in now. All right, so 18 sine 105. Okay, so we get 17.387. What did I just find? I found area. Area has a certain way that it's usually represented. What do we want to make sure we put on the answer so somebody looking at it knows it's an area? Besides putting an arrow and saying this is the area. We don't want to do that.
Inches squared or whatever unit.
Yeah, whatever unit it is squared. Inches, centimeters. We don't know the unit, so we'll just call the unit U. Unit. So it's 17.387 square units. Now, somebody looking at that knows that it is an area. Yeah.
So if it doesn't give you any sort of unit, you just always put U.
Generally, yes. Yep. Okay, so this is a side angle side triangle. And that's the formula you can always use to find the area of a side angle side. Because essentially, you found that dotted red line. You found the height by using sine. And you did 1/2 base times height. Right? It's just all built into the formula, so you don't really have to think about the trig part. You just have to plug into the formula and use it. Is there a question? Okay, so yeah.
So we can use this to find the side angle side.
You can use that to find the area as long as you know two sides and an angle between them.
So you can use that instead of the law of cosine. Or is that a completely different thing?
Well, this is to find the area of a triangle. Law of cosines is to find out how big an angle is or how big a side is. Yeah, so they're a little different. Now, what if I gave you one like this? Don't write it down yet. Are you given the information there that you would need to use the formula that I just showed you? Yeah? No, you are not given the information you need. But, well, so okay, what are you missing then? If you don't have the information you need, what's there? An angle. Any angle. Doesn't matter which one. You need two sides and you need an angle between them. How could you get an angle between two of the sides there? Yeah, you could do the law of cosines. So, the long way to do this problem would be use law of cosines, find an angle between the two sides, and then go back and use the formula I just showed you. Well, there's a shortcut. And the shortcut to figuring out the area of a triangle where you know all the sides is called Heron's formula. We don't go through the proof of this formula, but the proof involves the law of cosines. So this is the connection really with what we did in this section. We learned law of cosines. This formula is based off the law of cosines. That's Heron's formula. So it's the square root of, and then there's 4 letters under there, 4 unique letters. There's S, S minus A, S minus B, times S minus C. Well, we know what A, B, and C are. Those are the sides. What do you call it if you add up all the sides in a shape? Yeah. Perimeter. So if you take all the sides in a shape, add them up, and take half of it, that's called the semi-perimeter. So that's what S stands for. It's called the semi-perimeter. So it's not really that hard of a formula to use. You just have to find one thing first, find the semi-perimeter, and then fill in everything underneath the square root. It does not matter what order you multiply in. Under the root, you have S times S minus every side. You've got to do S minus A, S minus B, S minus C. Somewhere. So this is a shortcut to using the law of cosines, which you could do. So this problem I'm about to give you, you guys could all figure it out without this formula, but this is going to make it a lot faster. So let's say we didn't even know what A, B, and C are. It doesn't matter. Because the formula has S minus every side. Call A, B, and C whatever side you want. Again, the names of the variables are not what's important. It's the idea of how the formula works. Okay, let's start with the semi-perimeter. Okay, that's the first thing that you need to figure out. So add up all the sides. So 9 plus 7, that's going to give me 16. 16 plus 5 is 21. And what's half of 21? 10.5. Okay, so there's the semi-perimeter. Now let's find the area. Okay. What's going to go in the first set of parentheses underneath the square root? Lauren?
10.5 minus 7. Or, well,
You could. I mean, you could put the order of them in anything you want, but let's do it in the same order just so people can follow along with the formula.
so 10.5 minus 5.
I would put just the S first.
Oh.
Before we do any of the ones with the subtraction. I mean, you could put the subtraction first, but I'm going to keep this example following that pattern. So put the S first. So 10.5. Now let's do all the ones with subtraction. What's the next one that you could do? Yeah?
10.5 minus 7.
Yeah, you got to do 10.5 minus all of them. Do whichever ones you want first. So what's 10.5 minus, well, I'll just write that for now. Okay. What's going to go in the next one? Yep.
10.5 minus 5.
Sure. 10.5 minus 5. And what's going to go in the last one? Yep. 10.5 minus 9. All right. So let's type that in and see what we get. Okay, I'm going to do the subtraction so I don't have to type that in on the calculator. So square root of 10.5 times, what's 10.5 minus 7? Yep.
3.5.
3.5. What's 10.5 minus 5? Yeah. 5.5. And what's 10.5 minus 9? Yep. 1.5. I just don't want to type all that in because that's a lot of extra parentheses to have to put in everywhere. And that's what you type in. So the area of this triangle is about 17.412. And I don't think I had labels on the sides, so I'm just going to put square units. And that's how you find the area of a side-side-side triangle. Any question on that? Yes?
Did you say that you did the approximate sign because you're not sure of the entry distance?
Well, I'm sure of the way I rounded, but I mean, I don't have a way of writing this as an exact answer.
Yeah.
So I cut it off. Whenever you cut something off, it means it's approximate. But those are correct for what I wrote. So any questions on finding the area of a side angle side or side side side? Both of which you can really figure out without anything I taught you today. It's all based on Trig. So as long as you can somehow figure out the height of a triangle and the base of a triangle, you can find the area. It's just these formulas kind of speed that up a little bit. All right, so last part, what we're going to look at this week, sections 8.3 and 8.4. We're only going to do half of 8.4. So make sure if you are looking at the video because you end up being absent, look at the video from this year because I'm taking something out from last year. But 8.3 should be the same. We're going to keep all of that. So we're going to look at how we can write complex numbers a different way. And this different way helps us to do specifically multiplication and division faster. Addition and subtraction is pretty much already as fast as it can be. If you wanted to add those two complex numbers together, Remember, the first part is the real part, and the second part is the imaginary. What would you get in your final answer for the real part if you added those two together? Yep.
6.
6.
Plus 8i.
And then the imaginary part would be 8i. I mean, how are we going to do that any faster? It's already as good as it can be. So addition and subtraction, I would say doing something in what we call standard form. It's probably the best way to do it. But multiplication and division, that's a real pain in standard form. Remember, if you wanted to do multiplication, I might actually do one. Let me just see if I write one. Well, at some point I'll do one, but if you wanted to divide those two complex numbers, you can't just divide them. Okay, we actually have to do multiplication. Does anybody remember what you have to multiply the top and bottom by to do a division problem like that? Yeah.
I know you multiplied both the top and the bottom by the bottom, but don't you make the bottom positive?
Yeah. Does anybody remember what that's called when you make the bottom positive like that? 4 plus 5i? Yeah.
Inverse.
Not the inverse. Another word for it. Yep. It's a conjugate. Yes. Now, you have to do all that out, and that involves foiling. Okay. There is a trick to do the bottom. You're going to end up with 16 plus 25 in the bottom. There is no trick in the top. You have to foil the whole thing out. And if you forget the trick, you can always just foil everything else. But just to kind of review it quick, you get 12. You get 15i plus 8i. What's 15i plus 8i? Yep. So I get 23i. And then I end up with 2i times 5i. Does anyone remember what that comes out to? 2i times 5i. I won't say anything. Yep. That comes out to negative 10 because 2 times 5 is 10. I times I is I squared. And I squared is negative 1. So that comes out to negative 10. So even doing some of the steps as we go, we still have more to write. We've got to combine these like terms now. So 12 minus 10 is 2. Plus 23i. And 16 plus 25 is 41. Now we still haven't written the answer in what's called standard form. We're basically there. But to write it in standard form, you still have to do this. And that's the answer you get when you multiply or when you divide this by this. A lot of steps there. You got to remember the conjugate. You got to remember I squared is negative 1. You got to combine like terms. Then you got to separate it out into a real part and an imaginary part. Well, there's a much easier way to do all that. And the easier way to do all of that is to do that. Instead of writing complex numbers the way we're used to writing them, there's a different way to represent them, and it's called trig form. And that's what we're going to look at in section 8.3 and 8.4, trig form. The main thing that we're going to do in trig form is multiply, divide, and raise to a power. Because imagine how awful something like this would be. If you want to take a number and raise it to the 8th power, that means to write 3 plus 2i 8 times. Okay, you have 8 sets of parentheses with 3 plus 2i, and then you have to FOIL all of them. That's going to be a mess. Right? That's a lot of foiling if you have 8 sets of parentheses. It's still doable, but it may take you like 10 or 15 minutes. Now, if I did something like this, well, now you can't realistically FOIL 856 pairs of parentheses. You'll never get it right. It's just going to take you days. Well, if we use trig form for that number instead of standard form, whether you give me this problem or you give me that problem, I can do either one just as fast. It'll probably take me about 60 seconds to do the whole thing. But the whole key is getting away from standard form. All right. So to get away from standard form, one thing we have to know how to do is, if it's in standard form, I have to know the quadrant that it would be in, because quadrant is going to be important in a minute. Well, graphing a complex number is pretty straightforward. If you had a complex number written as a plus bi, it's basically like graphing the point a comma b. That's the idea. And what we do when we graph complex numbers is we have two axes. There's a horizontal and a vertical, but we do not call them x and y. When you graph something that's a complex number, we call the horizontal real, and we call the vertical imaginary. On the real axis, positive numbers go right, negative numbers go left, just like you're used to. And on the imaginary axis, positive imaginaries go up, negative imaginary numbers go down. So we're going to go through a few examples of how you would graph complex numbers on the complex plane. So here's my complex plane. This would be labeled as the real axis. That would be the imaginary axis. So you're going to start at the origin. And first thing is, you're going to look at this number and identify the real part. What's the real part of negative 4 minus 2i? Yep. Negative 4. So we're going to go left 4. And then what's the imaginary part? Yep. Negative 2i. So then that means we're going to go down 2. So left 4, down 2. And that's all there is to graphing a complex number in the complex plane. The important thing out of that is what quadrant are we in. So we're in quadrant 3. But that's going to be important. How about negative 2 plus 3i? What's the real part there? Yep. So we're going to go 2 to the left. And the imaginary part? Yeah. 3i. So we're going to go 2 to the left and
Up 3.
up 3. 2 to the left. So real part negative 2, imaginary part positive 3. Next, let's try. Yeah.
There's 1, so 0.
0. So you're not going to go left and right. We're just going to go in which direction to get to 5i. Yep. Up how many? 5. So that one's not in a quadrant, it's on an axis. Specifically, it's on an axis that represents 90 degrees going up. So that's what we're going to have to start thinking about. We're going to start thinking about an angle in a second. And what about 6? How would you graph that?
You would just go over 6.
Which way is over?
Oh, right.
1, 2, 3, 4, 5, 6. So there's no imaginary part, just a real part of 6, and that's on the axis that represents 0 degrees. So we want to start associating these with angles. That's part of it. And what do I mean by an angle? Like, look at 2 plus 3i. I mean, if you did something like this, and then you figured out that angle. That's part of what we need to do to write a coordinate, to write something in what we call trig form, if we're given standard. The other thing we have to know to write something in trig form is how far a point is from the origin. Now, the origin that we call it basically like your 0 point. When we talk about a number line in one dimension, what do you call the distance from 0? There's a name for it. Yeah? Absolute value. Well, that's the same thing we can call it here. If you wanted to know the absolute value of that complex number, what you're asking me is, what is the distance it is from 0? Well, we call 0 the origin. So if you could figure out the length of that line segment, that would be the absolute value of that number. It's the distance it is from the origin. Now, to figure the length of that line segment out, what kind of shape do you think we could make that would help us do that? Yep.
Triangle.
Yeah, we make a triangle. Like that?
No,
No, not like that.
that would not work.
That would not work. How would you do it?
Connect it to one of the other points.
Let me get rid of all these, so we're just focusing on one. So you said do what with it now?
I don't know what I would do with that.
How would you get the length of that line segment? Draw a line to one of the axes. Let's say like this. Okay.
Would it matter which axis? Like,
Yeah, generally go to the horizontal.
oh,
Yeah, do the horizontal. Okay. Now what do we know?
We have a right triangle.
Okay.
90 degrees.
Yeah, we have a right triangle. Anything else?
You know, two sides.
We know 2 of the sides. Yeah, what's this side? 4, yeah. So it's to the left, but yeah, it's still 4 units long. And what about this other side? Yep, it's 2. So how do you think you would figure out the absolute value of this point, which is the distance it is from the origin, which is really the hypotenuse of the triangle?
Pythagorean theorem.
Yep, we're going to use the Pythagorean theorem. So to find the distance between a point and the origin, again, that's called absolute value, distance from something to 0, you use the Pythagorean theorem. A is the real part, B is the imaginary part. So the idea of the formula, without using any letters, take the real part and square it. Take the imaginary part, which is just the number in front of the I. Don't use the I itself. Just the number, just the real part, and the number in front of I. Square it, add them up and take the square root. And that'll give you the absolute value of a complex number. We'll try an example. And I'm going to do one that comes out nice, but a lot of times because you are taking a square root, you can get answers that don't come out nice. As always, if you can reduce the square root, you should. Okay, let's try this one. If you're more visual, you can draw it. There is really no need to draw it. But you are about right here, and I want to know that. That's the absolute value, distance from the point to the origin. Okay. You don't have to give me the final answer, just what would be my formula to figure out the absolute value.
3 squared, or the square root of 3 squared plus 4 squared.
Square root of 3 squared plus 4 squared. So you're just using distances. Don't use the I. The I just means you went up or down. All I care about is how much up or down. It's 4. So 3 squared plus 4 squared. Okay. And what do you get when you simplify that? What?
Square root of 25.
The square root of 25. And when you simplify that?
5.
5. Good. So that's the answer. That is the absolute value of that point. And that's the other thing that you need to know to write a complex number in trig form. How far away from the origin is it? And what's the angle that it makes with the positive x-axis? Those are the two things. Okay, so let's look at this. So I've kind of told you the two things that you need to figure out, but let's write it down. So this is how we've been writing complex numbers so far. We've had a real part, and then plus or minus an imaginary part. And yes, I know normally we put the I after the letter, but the way your book does the formula, I put the I before it to make what I'm going to do match what's in the book. Technically, it does not matter if you put the I before it or after it. It's just for the type of thing that we're about to do, I usually comes before it. Okay, but that's standard form. Real part, imaginary part. To write it in what we call trig form, we have to get rid of this and this. We have to get rid of those two things. So I've drawn an example of what a complex number could look like if you graph it and it ended up in quadrant 1. What quadrant it ends up in is not important. Okay, not for what we're doing right here. You can think of the distance you are from the origin. Think of it like this. If you think of that distance now, it is a hypotenuse. But by drawing what I just did, I really made it a what? Yeah? Well, I made a circle. I don't know if it's a circle of radius 1 or not. But the hypotenuse there is really the, yeah?
It's an angle on the unit circle, so it's right back to the angle.
Well, yeah, we're going to have an angle here that we've traveled along a circle. So we don't know how much of an angle we're going to have, but it could be 20, 30, could even end up in quadrant 2 and be like 120. But my question is, this hypotenuse of the triangle is really something else in that diagram because of what I just drew. Yeah?
If it's a unit circle, then wouldn't it be 1?
Well, I don't know if that's a unit circle. I just drew a circle. So that dotted line here is really the what of the circle? Yeah?
The radius.
It's the radius. I don't know what the radius is. Could be 1, could be 12. But I drew a circle and I made that the radius. These are the two things that we need to use when you write a number in trig form. How far are you from the origin? So r is like the absolute value. And what's the angle that you rotated counterclockwise? Let's start by seeing if we can come up with something to substitute for x. What position is side x relative to theta? We're going to come up with a trig function. Yep, it's adjacent. And what position is side r? Yep, it's your hypotenuse. And what trig function involves adjacent and hypotenuse? Yeah, cosine. Let's start with that. So the cosine of my angle equals, what would be my fraction on the other side? What?
Adjacent over hypotenuse.
And if you substitute in our values for what you just said, you would have?
X over R.
Yep, perfect. X over R. So kind of like we did with the area problem, I want to know now, I want to get the x by itself. What would be in the box on the left if we get x by itself? Yeah. R times the cosine of theta. That is what we're going to substitute for x. Okay, in trig form, you are not allowed to use x and y. So that's how we're going to get rid of x. And now, what trig function would we use that would involve y? It's not cosine. Cosine involved x. So our choices are either sine or tangent.
Sine.
Yeah, I'm going to use sine. And can you tell me what the sine would equal in that diagram?
Sine theta equals y over r.
Y over r. Now, do the same thing we just did. What would be your formula for y based on the absolute value of the complex number, the radius, and the amount of rotation? R sine theta. So that is going to get plugged in right there. Actually, I wrote it right here. So x turns into r cosine theta, and y turns into r sine theta. If you make those two substitutions exactly the way that I'm pointing to them, you have r cosine theta plus, we didn't do anything with the I, so that stays right where it is, and y turns into r sine theta. Now, what do both of these have in common? The two things I just underlined. As far as a factor, they have a common factor. Yeah? Right. And when two things have a common factor, instead of writing the same thing twice, what we can do is factor it out and put the r in front and put r cosine theta plus I sine theta. And that is the trig form of a complex number. So to use that form, you need to know two things. You need to know the r, and you need to know the theta. So r is the radius. It's the distance from that point to the origin. What did we just learn in the last problem that calculates r? What did we call it? Yeah,
Absolute value.
the absolute value. Exactly. So r is the distance from the origin, which is really the absolute value. That's how you find r. And theta is the angle that you make with the positive x-axis. How do you find theta? Well, how do you find an angle in a right triangle? Use inverse trig. So if you were in quadrant 1, and your point was right there, you made a triangle, theta would look like that. That would be theta. If you were in quadrant 2, so let's say your point ends up over here, make your triangle. The angle that you want is this. You're probably going to find this first, which is fine. You can find that first. But then you really need to find the distance that the angle, or the angle with the positive x-axis. So you're always measuring from here all the way to your point. If you were in quadrant 3, it might look something like this. Make a triangle. You're probably going to find that first, but then what you really need is that, the angle with the positive x-axis. So we've done this before. This is getting into like the 180 minus, 180 plus, or 360 minus. Like if I knew this angle right here was 20, then I would say, well, it's halfway around plus 20 more. So I would say, all right, it's 200. Question on that formula, or what the r and the theta represent? Okay, so that's the trig form. So what we'll do with that is we're going to learn how to multiply two numbers that are written in trig form, divide two numbers in trig form, and then raise to a power. The hardest thing about doing that is making sure your numbers are in trig form first. Once they are, very easy. So we'll, I already did that, but we'll finish talking about trig form, and I'll write it down very clearly how to find r again. I'll put the Pythagorean theorem. We'll go through it one more time. These people don't quite get it. Okay. So the first part is going to be page 443. And second part, one, 2, and 3, that's a review of complex arithmetic, like conjugates, so we did that. 5 is okay. 8 is okay. 15. Okay, so we're gonna do that. So 1 through 3, 5 through 8, and 11 through 14 on page 4.
5 through 8 or 5 and 8?
5 and 8. Sorry, 5 and 8. So that's homework for tonight.